This is very exciting, ladies and gentlemen. I've just read part of a paper by Sudip Bhattacharya and Pankaj S. Joshi, two Indian physicists, on primordial naked singularities. Now, I've just emailed Pankaj Joshi because I want to find out more information about his idea. I want to find out whether or not we can potentially work with one another, since I think my ideas would go together like that with his own. I think he'd be a very, very interesting person to work with, and particularly since my own idea is riddled with naked singularities, of course, since we've got these clouds of electrons always in the background. These clouds of electrons, the electrons within the clouds, they're tunneling once every Planck time. So it's a decoherent universe. This is what leads to quantum decoherence. And in the background, you've got electrons tunneling all the time, constantly interacting with photons. You can imagine the electron as a sort of wave, just an oscillating two-dimensional sheet of something, right? And the photon is just a straight line that impacts it. When it impacts it, it crumples the sheet into an infinitely dense, so far as we're aware, point of mass energy, right? A finite mass in an infinitesimal of volume, therefore we get an infinite density, right? We get an infinite density. It's not that the electron and the photon are so heavy, it's that they're being squeezed into an infinitude of tininess, an infinitesimal point. So we have to start reviving ideas such as infinitesimals as well, which I've never really left our calculus, as I understand it, but has kind of left our physics to some extent. And I've been saying this also for years. I think we need to really revise our impressions of when and how to use infinitesimals in physics, and that we can have infinitesimal units in physics, and perhaps we can have infinities as well. Perhaps we can have an infinite universe, for instance. And I think so far as we'll ever know it's infinite. How about that for an answer to this question of, is the universe infinite or isn't it? I don't think we'll ever be able to know whether or not it is. From probabilistic methods that I've derived trying to calculate the true size of the universe based on the fullest extent over a finite period of time of electron tunneling, I come up with very, very large numbers indeed. But of course, if I make the time infinite in that calculation, I'll just get infinity out of the equation anyway, because it's multiplying something by infinity. So yeah, it will equal infinity again eventually. And assuming the universe is infinite in duration, which, I mean, if matter and energy truly can't be created or destroyed, which I suppose is the real big question behind that, isn't it? Does energy conservation hold on that level? If matter can't be created or destroyed, then the universe is infinite in duration, at least. It's infinite in extent, in temporal extent. So it has at least that infinity. Therefore, it might also be equal in spatial extent. I'm uncertain. I'm uncertain about spatial extent, or what we really mean by that. And that's a deeply philosophical issue in cosmology, I suppose. But yeah, back to naked singularities. This is something that's very central to my own work. I've been saying this for years about the Higgs boson. I've been saying this for years. I think the Higgs boson is a naked singularity. I think we see very great similarities between this Higgs event of two protons being slammed into one another, collapsing in on themselves into an infinitely dense point, I think, then releasing two gamma ray photons, which are the decay products we expect, the evaporation products we expect to see of black holes. So that makes a lot of sense, that they would evaporate in that way and give off gamma rays. What we've created is a microscopic dying black hole, or a naked singularity indeed, or something akin to a primordial black hole. But what a black hole would strictly be, which is different, is a black hole has an event horizon. And I surmise that for it to have an event horizon, you need to slam atoms together, not just protons. So that it keeps this electron density around it. So therefore you can have accretion of material. You can have something with a gravitational field that gives off an attractive force to objects in its surroundings. And also, if it can't find anything in its surroundings, will jump back into the black hole proper, pick up some energy there, a photon, then release it outwards, and from this we get Hawking radiation. So this is a Hawking radiation, a way of explaining that black hole information escape paradox that doesn't involve particle-antiparticle pair creation. It just involves an electron jumping into a black hole, snacking on a photon, it jumps somewhere else in the universe, releases the photon again. And this process, all these processes of these electrons doing this is stochastic. So it's it's not random as such. That's the thing. Like B.L. Hu in his paper that I read on stochastic gravity, that's not quite correct. And B.L. Hu admits as much towards the end of the paper. He might have said he's not quite gone deep enough with it, and I don't think he has maybe, but it's not more a microscopic theory of gravity, which it may well be indeed, yes. And the processes may seem very stochastic, but they're sort of demi-stochastic, I think, or semi-stochastic. It is a determining factor behind what causes a given electron to show up in a given place, and that's the energy of the electron that's preceded it, I think, in space. So, you get an electron with an energy determined by whatever photon it absorbs, right? That quantum tunnels to wherever there's another electron in the universe with a similar energy level, and the most similar energy level rather, and that one pops up in the location where the other one's just been. The other one emits the photon that travels off into space, absorbs another photon of a different energy, goes somewhere else. So yeah, I suppose you could call it stochastic actually. But then again, what is true randomness as opposed to whatever I'm describing? Because stochastic means random, basically. It means like a random distribution. Yeah, I suppose, if you were to map it out, it would create a Poisson distribution, wouldn't it? It would give us a stochastic distribution, yeah, it would. Well, that's physics, ladies and gentlemen. Very, very tough subject it is. And I'm hopefully going to have a lovely chat with Pankaj Joshi. I might try Sudip Bhattacharya as well if Joshi doesn't get back to me. But yeah, that'd be lovely, wouldn't it? Like if I actually got a PhD studentship in India, or went to study physics in India, I might well do that actually. I reckon it'd be quite affordable. I reckon I'd be able to afford it at least a year or so. Get a job out there teaching as well. Yeah, India, that'd be fascinating. Loads of rocket launches going as well at the same time. Pretty sweet. Okay, so that's my idea. Thank you about naked singularities. Thank you for watching. Bye bye. Love you lots. So yeah, very big news. Very good idea.